Welcome to the core of A2 computer science. This unit bridges the gap between theoretical algorithm design in Paper 3 and practical programming in Paper 4. You are moving beyond simple one-dimensional arrays into dynamic memory management, complex data hierarchies, and mathematical efficiency. If you want to write code that scales to handle massive datasets, this is exactly where it happens. Every time you use a complex application without worrying about how the computer's memory manages it, you are relying on the principles we are about to cover.
We begin with abstract data types. An abstract data type strictly separates logical behavior from technical implementation. You will master stacks using the last-in, first-out principle, and queues, which rely on first-in, first-out logic. You will learn to manipulate pointers for linear, circular, and priority queues, handling critical error states like overflow and underflow in your Python code. These are the fundamental building blocks for CPU task scheduling and expression evaluation.
Next, we break away from rigid structures. Linked lists use nodes and pointers to create dynamic structures that grow and shrink in memory. Then you will tackle hash tables. You will use hash functions to map keys directly to array indices and write the exact pseudocode required to implement collision resolution strategies like chaining and open addressing.
Data is rarely linear. Binary trees let you build hierarchical structures. You will trace pre-order, in-order, and post-order traversals for the examiner. Crucially, you will build binary search trees where the strict ordering property, left child smaller, right child larger, allows for incredibly fast search and insertion. You will manage the underlying pointers that hold the entire structure together.
Networks, maps, and social media all rely on graphs. You will represent directed, undirected, and weighted graphs using adjacency matrices and lists. Then you will navigate them. You will execute breadth-first search and depth-first search, and trace Dijkstra's algorithm using priority queues to find the absolute shortest path between vertices. Whether routing packets across the internet or finding the fastest route on a GPS, this is the algorithm that makes it happen.
To process these complex structures, you need recursion. You will write functions that call themselves, carefully managing base cases to avoid infinite loops and stack overflows. You will then apply this divide and conquer logic to advanced sorting. Both merge sort and quick sort use recursion to shatter large datasets into manageable halves before sorting them, vastly outperforming basic algorithms.
Finally, how do we measure an algorithm's efficiency? You will use big O notation to evaluate the upper bound of time and space complexity. You will analyze the best, worst, and average cases for all the algorithms you have built, proving mathematically why a quicksort outpaces a bubble sort as your input size grows toward infinity. You now know exactly what lies ahead. You will trace complex logic in exam tables and write object-oriented Python from scratch. This unit is the ultimate toolkit for A-level computer science. Master these data structures and you master the syllabus. Let's get started.